Okay, so today we are entering into a next phase of the CFD formulation. So far we have developed equations, differential equations which represent the flow. So this is what we have done. Earlier we started with governing equation, then we added to the RANS, Reynolds-Navier-Stokes equations, Reynolds-Navier-Stokes average equation. Okay, so now what we are entering into is that we have to discretize the domain, CFD domain, as well as discretize the equations so that we can actually operate on them. So we have a differential equation which we have to convert into algebraic form, and we have CFD domain which we have to discretize into smaller regions. How do we go about doing it? That is what we are doing here. So why do we need to discretize the CFD domain? That what is the issue before us? So the numerical solutions can give answers only at discrete points in the domain called grid points. Now when you are finding the numerical solutions, what you get, that if you have a grid here, let me just what do we mean by grid is that it's a, this is our CFD domain, okay, and so we will talk in terms of 2D only, because that is what we can put it on the paper. It is visible. You can correlate what you are seeing and what we are saying. In 3D it becomes slightly difficult to imagine what is going on. So this is a CFD domain and we are dividing it into number of cells, and these are the grid points. Okay, now when you actually solve this numerical solutions, what will happen? Either you will get solution at these points, right, which are called grid points, or you will get the solution at the center of the cell, right? So what happens is, when you are finding the numerical solutions, either you will get the solution at the grid points or you are getting at the center of the cell, depending upon how you are writing the equations. But when we talk in terms of these, let us say this area which is surrounding this, or in this case we are talking about this area, nothing is known about this when we find the numerical solution. How do you know about it? There is a way to know it, is that through the averaging. So if we know the values at this point, we can find the average at this point. So wherever you are, right? So suppose you want to find out value at this point, what you will do? You will take values at this point, these you know, okay, and you can take a weighted average and find the value at this point. Or in another case, suppose you are having a like this, you are finding the values at this point, this point, this point, that is center of the cell, and anywhere else you want to find the value. Suppose you want to find the value at this point, right? You can find the averages of these two. You want to find the, suppose you want to find the value at this point, right? You take this cell, you can say this value, and you can take this also and this also. Why not? You can make your mathematics and find the value. So in nutshell, what we are saying is, in a numerical solution, you do not get values at all the points. You get values only at some finite number of points, typically one for each cell, right? And for the remaining part of the domain, you get the values based on extrapolation or rather interpolation. You have values at two ends, you interpolate, you get the values in between. Okay, so coming back to this, now when you talk about analytical solutions, partial differential equations provide a variation of the dependent variable continuously throughout the domain. Now if you are going by the partial differential equation analytical solution, then what is going to happen? You are going to get value. If you have this domain, you are going to get value throughout this point. You will get an equation. You fill the value, so your value, suppose velocity, or you can say, rather let us say temperature, it will be a function of x comma y comma z. This is the equation you are going, and if you want to find out temperature at any point, you fill the value of x, y and z, you get the temperature, right? So it does not, you are not bound to put the value of x as only discrete values, 1, 2, 3, you can have 1.1, 1.2, 2.23, anything you want to put you can. So this is the difference between the two. Okay, but now the thing is, however, analytical solutions are not available in most of the cases. They are rare. So therefore we have to go for numerical solution. We are bound to. We have discussed this, because numerical solutions are not our first choice. We are forced, because our analytical solutions are not available for such set of complex equations. Okay, now when we go for numerical formulation, we have to actually discretize the CFD domain and also the differential equations governing the flow. So for numerical solution, we have to do both. So first we will talk about discretizing the domain. Second, we will talk about discretizing the equations. Okay. Now then, one general principle we can note that the more the number of cells in a grid, the more accurate the numerical solution is. So your solution, the quality of solution depends upon the quality of grid. The way you have discretized the domain, okay, that will determine the quality of the, we will discuss about it. But before that, we take these points. Now what are the information required for numerical solution? Now if we are trying to find the so first is discretization of the domain required dividing the CFD domain into smaller cells. So one thing we are doing is we are dividing the domain into smaller number cell. To be able to write equation for each cell and solve them by the computers, we need to convert this information into a form that can be used by computer. So we'll be writing equation for each cell, we'll be solving them, and that should be in a format which is readable by the computer, the way computer can handle it. Okay. Now for this, what we require, we have to name or number each cell. What is required is we have to give the name of each cell, because we have to identify. The computer will identify the cell by a name or a number. Normally it is a number, you can't give name. Even if you want to give name, it will be A1, A2, A3, A4, which is same as 1, 2, 3, 4 number. Because you cannot give so many names, different names, unrelated names you cannot give. But you can use that. Naming means you have to identify the cell so that you know, if you want to give instruction to the computer which cell to use, computer knows which cell you are talking about. You have to give the name. Then this cell is made up of nodes and its boundaries formed by the nodes. Now what is a cell? Cell is actually, if this is a cell, how do you know this cell? If you define these 4 points, if I don't talk about 3D, you assume that we are talking about 2D. Okay, so you have a cell in 2D. How do you define a cell? The 4 corners of it. If I know the coordinates of all the 4 points, I know the cell. Okay, so the cell is made up of nodes and its boundaries are formed by nodes. When I talk about the boundaries, these are the boundaries. These are the boundaries. 4 boundaries of the cell. Okay, now we need to know the coordinates of each node so that we can calculate the shape, size and orientation of all the boundaries of the cell. How would I know what is the area of the cell? What is the size of the cell? Orientation of the cell? What is the surface area of the cell? All that I can find out if I know what are the coordinates of each node. The 4 nodes, or in some case you can say your cell can be like this. Triangular cell. Then you have to know these 3 nodes. Here you are talking about 4 nodes. There you are talking about 3 nodes. But you have to know the coordinates of each one of them. Only then the cell is known. You see, the computer has to know in terms of numbers. Right? Okay. So then you require name or the number of the cells adjacent to it, neighboring cell. Now in CFD, when you write equation for one cell, it is actually in terms of the adjacent cell. Right? So if I go back to this diagram, suppose again I make a make it complete. So when we are talking about this cell and we are writing equation for this, then the value at this point, it is written in this term, this term, this term and this term. When you write equation for this cell, central cell, it is in terms of the adjacent cell, which means that you should know what are the adjacent cell in each case. Okay. Then we need to define a thread along which we have to move in the CFD domain, covering all the cell. Now you have to move from, because computer will be calculating one cell at a time. In a parallel processing, you may be doing 2, 3, 4 or whatever it is. Still, you are not solving all the cells together. One CPU will be solving one cell, or maybe if you, the way you write the program, it will be finite number, right? And you have millions of cells. Even if you are solving few number of cells together, maybe 10, 15, whatever way you are writing together, still there has to be an order in which they have to be solved. That order may be whatever order you decide, or the computer may decide, but you have to do one by one. So you need to define a thread, how the computer will move from one cell to another, right? In a simple case, what you can do, you can move from here to here, here to here, here to here, then here, then here, then here. You can go systematically, but still you have to decide. You might in another case In another case, you may like to go like this. This is what I am talking about. Thread. How you will move from one cell to another cell. Which cell, in what sequence you are going to sell them. Even if it is not important, it is required. Right? Because all the cells have to be solved. We have to tell the computer that which cell now to solve. Yes, you are given a one cell, it has solved it. Now, which cell to do? You have to tell it. So you have to tell after this cell, after this you have to do this, after this you have to do it. That means the whole thread you have to define. And whether that is being done automatically or you are telling it, but it is required. So all this information is required. Now, so there are two types of grids we come across. Right? One is called structure grid. The second is called unstructured grids. Grid is what? It's basically division of a domain into smaller cells. Right? Now, so this discretization can be done in two ways. Now, in general, discretization in x and y directions are different. Now, it is not necessary that the gaps between the cell or the size of the cell in both the directions should be same. X direction could be anything and y direction can be anything. That means your cell can be like this or it can be like this, in the simplest case. You get the point? So then indeed it is not necessary that delta x and delta y be the same, and it is also not necessary, let us say here, if suppose I am dividing a domain, right, I can divide it like this. On this side, x side, if I divide it like this, now if you take any cell here, right, delta x and delta y are not same. What I mean to say, delta x is not equal to delta y. It may or may not be equal to. Not only that, delta x1 is not equal to delta x2 is not equal to delta x3. Similarly, delta y1 is not equal to delta y2 is not equal to delta y3. It's not necessary, right? Only thing is you can have, okay. So it is also not necessary that discretization along any axis be separately uniform. So not only that, it is required that delta x and delta y should be same, it is not required that they should be in any direction, it should be uniform. It can be random. Okay. However, the majority of CFD applications use a grid which contains a uniform spacing in each direction, because this greatly simplifies the programming, saves the storage space, and usually results in greater accuracy. But if you divide it uniformly, what happens? You immediately know the next node. Suppose I know that each cell size is 1 centimeter. So I know the coordinates of all the points immediately. X is 0 centimeter, 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeter. I don't have to feed it. But if it is random, I will have to tell the computer that x0 is this one, x1 is this one, x2 is this one, x3 is this one, because there is no pattern in them. If there is a pattern, you can give the equation. If there is even you can have a quadratic equations for the delta x increasing with x. But there should be some relation. so that computer can use that and find the coordinates of the cell. So depending upon you either you give a relation or you give the values, right? Now recent research in CFD is focused on unstructured grids. So before that, let me say that when you contain the uniform spacing, then you get an advantage that programming becomes very simple, because the size of each cell is same, area is same. You don't have to calculate those areas again and again. If all the cells have same area, you can use that. You calculate it once and you can use it. But if all the cells are different, then you have to calculate area of each cell's surface every time.
So different area लेने के benefit क्या है?
आएंगे, we'll come to that. ठीक है? So recent research in CFD is what is called unstructured grid. Why do we go for non-uniform structures? Okay, not only non-uniform, haphazard. Although I shouldn't use the word haphazard, is something like, you can say, dynamic grids, where you actually decide, depending upon the result, what should be the size of the cell. Okay, there is no relation between the size of the grid as such. Okay, so unstructured grid, where the grid points are placed in a flow field in a irregular fashion. So unstructured grid wo hai. So what is the difference between the two? A structured grid is one in which you can find the coordinates of each cell by a relation. If you can put them in an equation, it is a structured grid. If I can define all the corners of all the cells with the help of some equation, it is a structured grid. That means there is a structure. Unstructured means there is no pattern between them. You cannot define the equation, which means that you have to define each and every cell. Okay. Now this is in contrast to structured grid, which reflects some geometrical regularity. So these are the one. Now why would we go for unstructured grid? Because there is advantage, and it is easy to discretize the domain using unstructured grid. It is very quick to establish. Structured grid, you take time to decide what should be the pattern, what is the equation. Unstructured grid, nothing, computer does it on its own. Small programs, computer makes its own grid. And the bigger advantage is that it can take any shape or domain. The structured grids are limited, that they can pick up only particular type of shapes. Unstructured grid can take up any shapes. Just for an example, if your domain is circular, I want to fill it with square grid. Right? Will all cell be square? What about this cell? This cell? It will be a mix of square cell or rectangular and triangular cells. Right? Which means that you cannot fill a circle with only rectangular cells. You have to use triangular cells. Right? And we will come across more cases where it will not be possible to use structured grid. Okay? So, and this can be a mix of structure and unstructured grid. No harm. You can have like that also. But you have entered into unstructured grids. Okay? Now you see example of structured grid. What is a structured grid? This is a structured grid, simplest structured grid. Now if you see here, each coordinate, the corner of each cell is related. The moment I define this, and if I define this, if I am able to define this and I am able to define this distance, that means delta y and delta x, right? Everything is defined, and I can tell what will be the coordinate of the, even naming is possible. तो मैं जो ये इसका जो नेम है आई जे है, इसका नेम क्या है आई प्लस वन जे, इसका नाम क्या हो जाएगा आई प्लस वन जे प्लस वन, इसका नाम हो जाएगा आई जे प्लस वन, दिस इज आई जे माइनस वन. So numbering is very easy, and value of, if you want to find out what is x and y value of each, it is easy. It's called structure grid. This is the simplest structure grid. Okay, and these are your unstructured grids. Now you see the shapes. This is an annular shape. You cannot fill it by any structure. Okay, although you can do it in the sense that you can, here if I take, I can do it this type of division, I can do radial and circumferential, I can do, and there can be some pattern. Okay, some shapes can be, but if you talk about this, you can't fill any pattern here, right? And when you talk about this, here it is talking about boundary layer. We will talk about why the unstructured grids are important. Okay, now so this is the example of unstructured grids. In all these examples you will find that each and every cell has to be defined, all the nodes of it have to be defined. There is no relation between the nodes. Okay, now we talk about what are the advantages and disadvantages of structured grid versus unstructured grids. So both have their relative advantages and disadvantages. As far as information is concerned, it is much easier to store the necessary information about the structure grid, as information can be fitted into mathematical relations. Structure means there is a mathematical relation, and all the information can be put in forms of equations rather than in terms of values. Okay, you take an example that when you talk in terms of steam tables and gas. Now for gas you just have an equation, you don't have to remember all the values, but for steam you don't have good equations, so they come in the form of steam tables, and so much value is there which you cannot remember, you have to use from the table. So in one case you are, if suppose you have to talk about the enthalpy, entropy of a gas, ideal gas, it's very simple, you know the formula, you can find out. But in steam tables what will happen? For enthalpy, internal energy, entropy, you have to use the table, right? So this is the difference. In case of unstructured grids, as there is no mathematical pattern, a lot of information about each cell of the grid is required to be stored. So you require more memory. Although in unstructured grids, computers develop the grid on their own, so you are not doing any effort, but the memory of the computer is being used. Okay. Now, ease of discretization of domain. However, all shapes are not amenable to structured grids. For all types of domains, you cannot put them in the structured grids. But you can have a mix of structure plus unstructured grid, that you can do. Unstructured grids are easy and quick to formulate. Unstructures are quick, because they are done by computer. Right? If you have to do it, it will take a lot of time, more time than the structure grids. But computer is doing it. It becomes fast because computer is doing it fast. It's not that it is easier. It's only that computer can do it. And for structure, you have to tell the computer that this structure has to be followed. Even that, giving it that much information will take more time than computer doing it on its own. While it is much more difficult to set up unstructured grid. Right? Now, computers can automatically generate unstructured grid as well as structured grids. There are computers, there are programs, even structured grids they can do on their own. There is nothing like structured grids cannot be made. They can also be made. Okay. Now the main thing is something called grid adaptation and dynamic grid adaptation. This is important. Why unstructured grid becomes important? Okay. Now, what is grid adaptation? Grid adaptation means you are making grid as per the requirement of the problem. You are adapting your grid. Adaptation. I normally tell my students is that when you want to learn anything, you learn the meaning of the word used. It is easy to remember. So what it does mean, adapt. Adapt means to change as per the circumstances. That is the meaning of adaptation. So this grid adaptation means the grid can change as per the requirement. Right? Now, unstructured grids can be freely adapted as per the need of the problem. Structured grids can also be adapted, but the freedom available in unstructured grid is much less. What does the adaptation means? Let me tell you first, because then only it will become important. This is, I have a domain like this. Simple structure grid. Okay. What does grid adaptation means is, I find that this cell size is bigger. I can divide it into. I find this is still bigger. I can divide it further. Depending upon my need, I will reduce the size of the cell. And also, I can join the cell. These 4 cells will become one cell. What does that mean? That instead of doing my solution for 4 cells, I am doing only for 1. So I have reduced the number of calculations. Because the total amount time will be taken will depend on what? The number of cells. So if I reduce the number of cells, my overall simulation time will go down. If I increase the number of cells, the simulation time will go up. So what I do, I put the cells as per the requirement of the solution. Somewhere more sizes, somewhere less size. Right? Whenever I will increase the size, the number of simulation time will reduce. Whenever I will reduce the size, simulation time will increase. This is called grid adaptation. Right? But you will notice here that I can break a cell either into 4 parts or join the 4 cells. Right? Now take another case. Again a domain, and this has a cell like this. Of course, it is totally filled. Now I can reduce the size of these cells like this. Just I can double it. So I don't have to go 4 times. I can only simply double it. That is the freedom. And also sometimes if I have to join it, suppose this is the cell, right? What I can do, I can delete this. It will become one cell. Right? So this is called grid adaptation. Why do I do it? That question remains. That question still remains. Now why do I do it? Why do I break the cell in a smaller part or join the 2 cells? That is the reason. Now the thing is, suppose you have a domain like this. Now I have divided this cell into smaller parts. Domain. Now if my flow is almost uniform here, then I don't need so many cells, because everywhere this value is same. So whenever gradient of a parameter is small, that means variation in any parameter is small, the flow is uniform, it is tending towards uniform, I can take less number of cells. And where there are steep changes, right? Wherever you have del phi I by del xi, these are gradients. Phi I is any parameter, xi is any dimension. Now if they are very big, then what you will have to, you have to capture that. The flow is bending like this. If I have to capture this, I have to take smaller cells. If the flow is like this, I need only this cell. This is enough to tell me. And my simulation time depends on the number of cells. So what I am doing, wherever the more number of cells are required, wherever the gradient is high, there I will put more cells. Wherever gradients are less, I will put less cells. Which means that I am optimizing in the simulation time. So I get the best solution with the least time. And that is why we go for grid adaptation. Okay. Now you see this diagram back, you will see that everywhere the sizes are same, different. You see here, this is a boundary layer. A boundary layer, there are fast changes. You want to capture there. So you have cells coming very close to each other. And in the far region, where you find it, the flow will be less violent or less changing, less of gradient, you go for bigger size of cells. Similarly, you find this place. You find here the things are changing very fast. These are the critical regions. You don't want to miss anything here. You make the grid smaller, right? Otherwise, you make it bigger. Bigger, you will always like to make it bigger and bigger and bigger. If there is only one cell, okay, fine. You don't have to do much calculation. But the problem is you won't get the result. So the quality of the result depends upon the quality of your grid. Because each grid is going to each cell is going to tell you only one value, right? So you have to see that in how many values you can represent a flow or a domain. This is the thing. Okay. So we come back to this. What is grid adaptation? Grid adaptation is unstructured grid can be freely adapted as per need of the problem. In grid adaptation, the unstructured grids are much easier. You can join anywhere because each cell is independent. Right? There is no formula to define the coordinates of the cell. If you just join two or split the two, create new coordinates. Okay. As a result, the overall number of cells required to discretize the CFD domain may be less. Moreover, the solution to the problem may be more accurate as we can modify the grid as per the gradients present in the flow. So what we are doing, wherever there are steep gradients, we are putting more cells there. Where there are less gradients, we are putting less number of cells, and in a way we are optimizing our solution. So we get a good solution despite being less number of cells. In structured grids, the problem is slightly tricky because you cannot very much change the number of cells. In fact, you change it because there is a pattern. So even if you try to change, you change at many places where it was not required. You have to change there also. So the freedom available to you is less. Structured grid also can be adapted, but there the freedom is less. And this all thing is done by the program. CFD program, they do it on their own. So you can just imagine that how much they would have labored to do it. So what is happening in a CFD program, after you are given the equation, they solve the equation, find the gradient, and then they automatically change the size of the grid and then again calculate it. And dynamic grid adaptation means you keep on changing it. So after 100 iteration or maybe 1000 iteration or whatever you decide, you make a new grid. You solve it. You get a new data and you find that now you require more concentration here or more gradients are here, you will increase the number of cell here. At a later time you find no, you want somewhere else also, you can do it. So that type of thing, program does it on its own. So you can imagine the people who would have developed this program. Right? CFD softwares are capable of dynamic grid adaptation, that is, grid can be adapted as per the need. So to minimize the number of grid points with the best results. These programs can do it. So what we have done is, we have told you what is grid adaptation, what is structured grid, what is unstructured grid, what is the use of that, what are the limitations, what are the issues involved. Practically, you will not be doing it unless until you write the whole program. Right? So, but at least you know that what is happening in the software. Okay. So, we will stop here and